we can calculate the molar mass of a gas experimentally. And this can be used for a gas or for an unknown volatile liquid. And we'll actually be doing an experiment like that next week. So to find the mass, the molar mass of an unknown volatile liquid, you'll take a weighed sample and heat it until it becomes a gas. So you know the mass of it is a liquid, then you heat it until it all becomes a gas, and then you can measure the temperature, pressure, and volume of the gas, and that gives you the information that you need to calculate the moles of gas. Knowing the moles of gas, and you already measured the mass, you can calculate the molar mass. So let's do an example. A sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. So again, we want to identify all the numbers that were given. So we have a mass there, and a volume, and a temperature and a pressure. And then identify what are we trying to find. So we're trying to find the molar mass. So we can take these numbers that were given and write them down and identify what they represent. So we have 827 milligrams. And 0.270 liters, 88 degrees Celsius, 975 millimeters of mercury. So this last one is the pressure, right? It actually says that in the problem, the pressure of 975. So I'm going to call that P. And going, working backwards here, 88 degrees, that's the temperature of the gas. 0.270 liters is the volume of the gas. And 827 milligrams is what? That's the mass, right? So the mass of the gas is equal to this. Now, normally we don't have the mass of a gas in a gas law problem, but we'll see in a minute why we need that. And then we're looking at, we're supposed to find the molar mass. We ask ourselves, what does molar mass mean? How do you calculate molar mass? What are the units? It's grams over moles, right? So it's mass in grams divided by amount in moles. So this is the mass that we need up here, but is it in grams? No, it isn't. Well, we could convert that to grams though, can't we? So grams up here, milligrams down there. Milligram stands for times 10 to the minus 3. So 1 milligram is 1 times 10 to the minus 3 grams. We get 0.827 grams. There's more than one way to think about these metric unit conversions. It doesn't really matter how you do it as long as you can do it correctly, reproducibly, right? So if you're still getting those backwards sometimes, please come and talk to me and we can explore other ways that might make more sense to you. Because that is an important thing, the milli and the kilo especially. Okay, so mass in grams, that's something that we need. So there's our mass in grams. And we can still read that. And that's going to go up here. So the other piece of information we need is the moles. How can we calculate the moles of gas? We can't use the molar mass. We don't know the density. PV equals nRT. Yeah. So we're going to use the ideal gas law. PV equals nRT. So we have P and we have V and we have T. And R is a constant that we can just look up. So R is 0.08206 liters times atmospheres divided by moles times Kelvin. And then what we're looking for is N, right? N is the amount of substance in moles. So we can rearrange this here, dividing by RT on both sides. So N is going to equal to the pressure times the volume divided by R times the temperature. The units on the ideal gas constant are important. They tell us what units we need to use for the other things in the equation. Is liter a good unit for volume? Yeah, because liter is here. How about degrees Celsius? We need kelvins. So let's convert that to Kelvin. Not going to trust my brain today. 361. And then the pressure, it was given in millimeters of mercury, but the units on the ideal gas constant tell me it needs to be in atmospheres. So we need to convert that one as well. Pressure unit conversions are always just one step. So I want atmospheres. I'm going to divide by millimeters of mercury. I can look this up if I don't remember. 1 atmosphere is 760 millimeters of mercury. So, and I get 1.28, and I'm going to write down 2 extra digits, and that's my atmospheres. So now I have pressure, volume, R, the gas constant, and temperature, and all the units are going to match up with what's in the ideal gas constant. So I can put these numbers into my equation and find out how many moles of gas there are. Do you see what I did wrong? I put temperature up here instead of volume. Let's try that again. Mm-hmm. Usually it's what? Well, it depends on how many significant figures you use. So yes, the ideal gas constant is known to more decimal places. So you mentioned 0.082058, something like that. Yeah, so our book uses 0.08206. Some textbooks even use 0.0821, which is only 3 sig figs. But this is the one that our textbook uses, and so that's the one I'm using. You can use more digits. That's always fine. That's a good question. Anybody else have any questions? Yeah.
Oh, it's just for the calculator, because I haven't used this one before. What does the E mean?
Okay, so if you get a number on your calculator, here, let's do this calculation. So remember when we're doing this, we're multiplying the top. And then the way most people think of it is that you're dividing by this times this. And so if that's how you think of it, you need to use parentheses down here. if you're gonna put a multiply sign in there. So times 0.27. So I'm coming up with 0.01169 moles, which is different than the number you got. Anybody else get this number? This one? Okay. So the number that you got, which is a whole bunch of numbers, and then over here it says E something, right? Maybe E minus 3 or something. This is how that particular calculator tells you scientific notation.
Oh, so that's like.
So the E minus 3 is times 10 minus 3.
Okay.
Yeah, and you always want to look way over to the far right side of that number to make sure that you're not overlooking the factor of 10, because you can have something like 5 times 10 to the 37, right? And it's 5 point blah 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 blah. And if you don't look at the end, you don't see the E37, and now you're like way off. So always check for that. So if you did not get this number, you're probably having an issue with this dividing by these things multiplied. So again, you take this number times that number, divide, open parentheses, this number times this number, and then close the parentheses and press equals. The other way you can do it, just depending on which calculator you have, there are calculators that will give you a format like this. And so as you type it in, you can type it in and this line will be here, and then on the bottom you can just type the two things multiplied and it'll give you the correct answer. So that's another way to use a calculator. You just need to find what works for you and do that consistently. But this is what most people do. That'll work on any calculator. Any questions?
I keep getting the same thing.
You keep getting the same thing? Okay,
Yeah.
Let's see what's happening here.
Sorry. I tried it like multiple different ways.
Oh, okay. So what you're getting is 1.1693 blah 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 E negative 2. So over there. So if I take this number, this is in scientific notation, 1.1693 times 10 to the minus 2.
Oh, okay.
Yeah. So this is in decimal notation. If I move the decimal point 2 places, I'm going to get, here, let me see your calculator. So on the TI-30X Pro, if you press mode, and then go down to the second line, there's norm and psi and eng for engineering. And I'm highlighting norm, and I'm going to press enter, and I'm going to quit. And, well, it's hard to find the exact placing of that. Maybe this one. There you go.
Thank you.
Okay. So most calculators, for numbers that are close enough to 1, you can tell it to display either in scientific notation or decimal notation. But then it tends to stay that way until you change it, and so sometimes it's kind of annoying. Okay, any other questions? We're not quite finished here. I still need to do that, that's okay. So now I've got the amount in moles, and that's what I need in the denominator to calculate my molar mass. So I'm going to put those numbers in there. The mass was, where'd it go? 0.827. grams divided by 0.001, whoops, too many zeros. 1,169 moles. So 0.827 divided by the number of moles, and rounding this to 3 significant figures, I'm going to get 70.7. Yeah. Mm-hmm. So for the pressure, where did I get this from, right? So the units on the ideal gas constant show atmosphere for the unit of pressure. I was given millimeters of mercury. So I need to convert from from millimeters of mercury to atmospheres. And if we look that up, we see that 1 atmosphere is equal to 760 torr, which is equal to 760 millimeters of mercury. So that's where the 760 came from. It can make your problem solving go faster if you memorize that one. There's 2 different units there, torr, millimeters of mercury. They're different names for the same thing. But there's only the one number, 760. And that's the one that gets used the most. It will be given on an exam, but it's a lot faster if you have it in your head. Don't have to look it up. Yeah. Pardon me? There is that equation that the book gives with the capital M, and that will give you the same answer. I don't like that because that's another equation to memorize. And I think it's better to just stick with the basics and learn how to put pieces together. Yeah, but that the other equation works. Yeah. Any other questions? So here's another example. This one is a lot like the data you'll have from experiment 6A. An organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask. She closes the flask and re-weighs it. Her data is given below. Calculate the molar mass of the liquid. So this problem's a little different in that it's got this, story here, a whole bunch of words up here. We kind of need that so that we know where these numbers came from, but we already have all the data pulled out and labeled for us, so that's kind of nice. So here we have the volume of the gas, the temperature of the gas, the pressure of the gas. So could we calculate the moles of gas in the flask? Yeah, PV equals nRT, right? PV equals nRT. And when we rearrange, we get N is equal to PV over RT. Are the units what we need? No. Ever wonder why they keep giving us the wrong units? They're not just being mean. These are the units that you would use to measure those quantities. But these, they're not the units that are in the ideal gas constant, because those are more metric base units or SI base units. So these are just really common conversions that we need to get comfortable with. So we need to change milliliters to liters. So 1 times 10 to the minus 3, 3 liters is 1 milliliter. And so this is 0.213 liters. 100 degrees Celsius, what do we need to change that into? Kelvin, right? This time our temperature has 1 decimal place, and so then I think it's more appropriate to use 273.15 instead of just 273. because now we're not just ignoring those decimal places. So this is going to give us 373.15 Kelvin. And the pressure is given here in torr. Torr is a different name for millimeters of mercury. It's the same relationship. We need to convert that to atmospheres. 1 atmosphere is 760 torr. So I want to make sure I keep the correct number of significant figures, and then ideally keep 2 extras. And move that over. And then, of course, we do need R. 0.08206 liters times atmospheres divided by moles times Kelvin. So we can plug our numbers in here. 0.213 liters. That was the volume. 0.99211 atmospheres. It would give me the same answer if I put the volume first, but I just want to avoid any extra confusion. And my temperature's down here. So I'm getting a small number for the amount of moles, 0.00690 moles. Make sure that you're communicating with your calculator correctly to get that number. So we're trying to find the molar mass. And just like in the previous problem, what we want to do is ask ourselves, well, what is molar mass? What are the units of molar mass? It's the mass in grams divided by the amount in moles. So we just found the amount in moles. So there's our amount in moles. We can go ahead and write it up there if we want. And then the other thing that we need is the mass. The mass isn't given to us here. We're given information, right? So here's the mass of the empty flask, and here's the mass of the flask with the gas in it. How do we find the mass of just the gas? We're going to subtract, right? So we take the flask plus the gas, and we subtract the mass of just the flask. So we're subtracting these guys. 78.416 minus 77.834. And so that's 0.582 grams. Whoops, not sure how that happened. So that's the mass, and we want that to be up here. 0.582 grams. so I'm gonna do the division there, and it should have 3 significant figures, so 84.3 grams per mole is my molar mass. When we're weighing things in the lab, most of the things do not like to stay on the balance by themselves. Just like a puppy is not going to stand still in the balance, you can find out how much it weighs so you can give them the right amount of medicine, right? You're not going to get some water to sit on the pan while you weigh it, right? It's going to run off, right? A gas is going to escape and go all over the place. It has to be contained in a flask. Even solids, we often weigh on something else because they're little pieces and we don't want to have to try to pick up all those pieces off the balance pan. So almost always when we're looking at masses with an actual experiment, it's going to involve some subtracting. Okay, and that's a mistake that students often make. They've measured this, and so they use that in their calculation for the mass of the gas, and that ends up with a wildly incorrect number. Very understandable, but still not right. Any questions? Oops. Yep, so that's where we were supposed to finish last week.